Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square ABCD, and we know that the size of one side of square ABCD is equal to 8 units, and inside the square we have two circles. The radius of this big circle is 2r, and the radius of the small circle is r, and we want to find out the size of r, that is the radius of the small circle. Okay, but before that I present to you two new rules. The first rule, rule number 1, states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So I will read rule number 1 again. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So actually the meaning of rule number 1 is that if you have a circle suppose that the center of this circle is at point M, and we have tangent to this circle actually tangent AB is tangent to this circle at this point. Suppose that this point is point O, and from the center of the circle we will draw a radius that is drawn to the point of tangency. This is the radius, OM is the radius of this circle. So according to rule number 1, a radius, this radius that is drawn to the point of tangency, actually the tangent AB is perpendicular to this radius that is drawn to the point of tangency, that is to say point O. Point O is the point of tangency, and we have this radius that is drawn to the point of tangency. Therefore the tangent AB is perpendicular to the radius, that is to say this angle equals to 90 degrees. as this angle also equal to 90 degrees. This angle equals to 90 degrees, so whenever you have a radius that is drawn to the point of tangency, that is to say point O, then the tangent will be perpendicular to that radius, that is to say this angle is 90 degrees and this angle is also equals to 90 degrees. Okay, so actually that is rule number 1. And we have also rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So I will read rule number 2 again. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. Okay, so what is the meaning of rule number 2? Actually, rule number 2 states that if you have a square, if you have a circle, and from an external point to this circle, actually this point, that is point P, is an external point to this circle because it is not located inside the circle, it is not located on the circle, but it is located outside of this circle. Therefore point P is an external point to this circle, and if from point P you draw two tangents to this circle, so this will be the first tangent. We will define the touching point between the tangent to this circle as point A, and we will also draw a second tangent from point P to this circle. We will do it again. We have a circle. And again, here point P is an external point to this circle, and if from point P we draw two tangents to this circle, we will define the touching point between the tangent to the circle as point B, and we will draw another tangent to this circle, and we will define the touching point between the tangent to this circle as point A. So according to rule number 1, the lengths of these two tangents are equal to each other. That is to say, PA, that is the length of this tangent, is equal to PB, that is the length of the second tangent. According to rule number 2, PA equals to PB, because whenever you draw two tangents from an external point to a circle, then the length of those two tangents will be equal to each other. That is to say, PA will be equal to PB. Okay? So, in the next step, we will define the center of the small circle as point P, and we will define the center of the big circle as point Q. And we will join together points A and P by a straight line. And we will draw radius from point P to the, first of all we will define the touching point between tangent AB to the small circle as point M, and we will draw radius from point P to point M. Actually, this radius of the small circle is drawn to the point of tangency, that is to say, it is drawn to point M. Therefore, the tangent is perpendicular to this radius, that is to say, this angle is a right angle. It equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. we will define that, first of all, we will define this point as point E, and we will define the touching point between tangent AE, this tangent, to the small circle is point F, and then we will join together points P and F by a straight line. Actually, PF is the radius of the small circle because line segment PF exits from the center of the circle, that is to say from point P, and touches the circle at point F, therefore it is the radius of the small circle. I will name it as R. And in the next step, so actually this radius is drawn to the point of tangency, that is to say point F. Therefore the tangent AE is perpendicular to this radius that is drawn to the point of tangency, that is to say this angle is 90 degrees, and this angle also equals to 90 degrees because of the fact that this radius is drawn to the point of tangency, that is to say point F. Therefore the tangent AE is perpendicular to this radius that is drawn to the point of tangency. So this angle is 90 degrees and this angle is 90 degrees according to rule number 1. So in the next step we will prove that the right triangle AMP is congruent to the right triangle APF. Again, the right triangle AMP, we will prove that this right triangle AMP is perpendicular to the right triangle APF. I will repeat again. We will prove that the right triangle AMP is perpendicular to the right triangle APF. First of all, we know that AM equals to AF. AM equals to AF according to rule number 2. Because we have here point A that is external point to the small circle, and from point A we have two tangents to the small circle, tangent AM and tangent AF. So according to rule number 2, if from one external point you draw two tangents to a circle, then they will be with the same length. That is to say AM, tangent AM equals to tangent AF. For the length of those two tangents to the small circle, they have exactly the same length. That is to say AM equals to AF. According to rule number 2, AM equals to AF according to rule number 2. And we also know that PM equals to PF equals to the radius of this circle. PM equals to PF equals to the radius of the small circle. Again, PM equals to PF equals to the radius of the small circle, and we have a common side AP, side AP is a common side, it belongs to both triangles. So AP equals to AP. Side AP is a common side that belongs to both triangles. Again, AP equals to AP is a common side that belongs to both triangles. So we actually proved that all the three sides of the right triangle AMP are correspondingly equal to the three sides of triangle, the right triangle APF, 1, 2, and 3. Okay? Therefore, we actually proved that the right triangle AMP is congruent to the right triangle APF according to side rule. So I will write it down. We proved that the right triangle AMP is congruent. This is the sign of congruent to the right triangle APF according to side rule. So what is side rule? Side rule is if you prove that three sides of one triangle are correspondingly equal to three sides of another triangle, then you actually proved that those two triangles can belong to each other according to side rule. Okay, and from the fact that those two triangles can belong to each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that states that corresponding angles in congruent triangles are equal to each other. Those two triangles can congruent to each other, therefore those two corresponding angles will be equal to each other. That is to say, angle PAM, this angle, is equal to angle PAF according to the rule that corresponding angles in congruent triangles are equal to each other. And if we define this angle as alpha, then this angle will be also equal to alpha because of the fact that they are equal to each other. So actually we found out that angle PAM equals to angle PAF, and both angles are equal to alpha according to our definition. Okay? So in the next step, we will connect together points A and Q by a straight line. We will define the touching point of the tangent AE, the touching point of tangent AE with the big circle will be defined as point L, and we will join together points Q and L by a straight line. QL is the radius of the big circle, that is to say it equals to 2r, because of the fact that line segment QR exits from the center of the circle and touches the circle at point L. Therefore, it is defined as the radius of the big circle. It equals to 2r. And so actually we have here this radius that is drawn to the point of tangency, that is to say to point L. Therefore, the tangent AE will be perpendicular to this radius according to rule number 1. So this angle equals to 90 degrees and this angle also equals to 90 degrees. Again, because of the fact that this radius is drawn to the point of tangency, that is to say to point L, then the tangent will be perpendicular to this radius according to rule number 1. That is to say this angle is 90 degrees and this angle is also 90 degrees. And the same thing is true for this radius. This radius is drawn to the point of tangency. We will define the point of tangency of tangent AD with the big circle as point S. So we have the radius QS is drawn to the point of tangency, that is to say to point S. Therefore, the tangent AD is perpendicular to this radius that is drawn to the point of tangency according to rule number 1. That is to say, this angle equals to 90 degrees. It is a right angle, and this angle is also equal to 90 degrees. Okay, so in the next step, we will prove that those two right triangles can go into each other. So, actually, we will prove that triangle AQL, this right triangle, is congruent to the right triangle, triangle AQS. I will repeat again. We will prove that the right triangle AQL congruent to the right triangle AQS. Those two right triangles, we will prove that they congruent to each other. First of all, we know that AL equals to AS. AL equals to AS according to rule number 2. Rule number 2 says that if from external point of a circle, that is to say point A, we draw two tangents to this big circle, then this is the first tangent and this is the second tangent, then the length of those two tangents will be equal to each other. That is to say AL equals to AS. So AL equals to AS according to rule number 2. And we also know that QL equals to QS equals to the radius of the big circle, that is to say 2R. QL equals to QS equals to the radius of the big circle, that is to say 2R. Again, QL equals to QS equals to the radius of the big circle, that is 2R. And we also have a common side. QA is a common side. It belongs to both right triangles. So we can write down that QA equals to QA is a common side that belongs to both triangles. Again, QA equals to QA is a common side that belongs to both triangles. So we actually proved that all the sides, 3 sides, 1, 2, 3 sides of the right triangle AQL are correspondingly equal to the 3 sides of the right triangle AQS. Therefore, we proved that those two right triangles can go into each other according to side rule. So I will write it down. We actually proved that the right triangle AQL is congruent to the right triangle AQS according to side rule. Okay, and from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding angles, those two corresponding angles will be equal to each other. That is to say, angle QAL is equal to angle QAS. And if we define angle QL as beta, then angle QAS will be also equal to beta. So we actually found out that angle QAL equals to angle QAS, and both angles are equal to beta according to our definition. Okay. Actually, we know that a square has four right angles. So square ABCD has four right angles. That is to say, this angle is a right angle. It equals to 90 degrees. We will define this point, the touching point between tangent BC to the small circle, as point H. And here we have this radius is drawn to the point of tangency, that is to say point H. Therefore, the tangent BC will be congruent to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. So in quadrilateral PHMB, in quadrilateral PHMB, this quadrilateral, we have three right angles, 1, 2, 3. And the sum of three right angles is 3 times 90, it equals to 270 degrees. Okay, so in quadrilateral PHMB, we have three angles that the sum of them is equal to 270 degrees. And so what is the side of the fourth angle? We have the rule that the sum of the angles in any quadrilateral equals to 360 degrees. So if we define this angle as angle Z, Then the sum of three angles that equals to 270 degrees plus the size of angle Z in total must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. So we will subtract 270 degrees from this equality, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that angle Z equals to 90 degrees. So I'll write it down that the size of angle Z is actually, it is a right angle, it equals to 90 degrees. So as you can see from the drawing, quadrilateral PHMB has four right angles. Okay, so, and we have a rule that any quadrilateral that has four right angles, it must be at least a rectangle. Okay, so quadrilateral PHMB is at least rectangle. Any quadrilateral that has four right angles, it must be at least rectangle, if not square. Okay, so quadrilateral PHMB is at least rectangle, and we have a rule that states that the opposite sides of any rectangle are equal to each other. Opposite sides of any rectangle are equal to each other. That is to say, PM equals to HB, PM equals to HB, according to the rule that is stated that the opposite sides of a rectangle are equal to each other, PM equals to HB. But we know that PM equals to R. PM equals to R, therefore we can derive from this equality that HB also equals to R. HB also equals to R. So here HB equals to R. Okay. We also know that PH equals to R. It is the radius of the small circle. PH equals to R. But according to the rule that the opposite sides of any rectangle are equal to each other, PH also equals to MB. So PH also equals to MB. PH equals to MB. So from this equality, we will derive that MB also equals to R. MB equals to R. So actually we found that all the sides of quadrilateral PH MB are equal to each other, they are all equal to R, and quadrilateral PHMB has four right angles, therefore it is not rectangle but square. Okay, so quadrilateral PHMB is a square. Okay, and we know that the size of any side of square ABCD equals to 8 units. This is given us that AB equals to 8 units, so all the sides are equal to each other, so all the other sides are also equal to 8 units. So AB equals to 8 units, according to what is given us in the question. So we can draw here that AB, the size of AB is 8 units, and MB equals to R. Okay, so what is the size of MB? AM, the size of AM is actually the size of AB minus MB. Again, the size of AM is the size of AB minus MB. That is to say, AM equals to AB, that is 8 units, minus MB, that is R. So actually we found out that AM equals to 8 minus R. Okay? And we will find out also the size of AS. First of all, we will define the touching point between tangent DC to the big circle as point N. The touching point between tangent DC to the big circle will be defined as point N. Then we'll join together points D and N by a straight line. Actually, QN is the radius of the big circle because of the fact that line segment QN starts from the center of the circle, that is to say point Q, and ends at point N, that is a point on the circle itself. Therefore QN is the radius of the big circle, that equals to 2R. And we also know that this radius is drawn to the point of tangency, that is to say point N. And according to rule number 1, when you have tangent to the circle, this is tangent to the circle, and we have this radius that is drawn to the point of tangency, that is to say to point N. Therefore, this tangent DC is perpendicular to this radius. That is to say, this angle is 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. And we know that all the 4 angles of a square are right angles, they are equal to 90 degrees, that is to say angle ADC equals to 90 degrees. It is one of the angles of square ABCD, therefore it is equal to 90 degrees. And again, if we define this angle as angle Z, we know that in quadrilateral ADSQ, the sum of the angles in any quadrilateral equals to 360 degrees. Okay, so the sum of the angles in quadrilateral ADSQ must be equal to 360 degrees. but we have already three angles that are right angles. These three angles are right angles, so the sum of three right angles is 90 degrees times 3 is 270 degrees. So actually the sum of the angles in quadrilateral ADSQ it is actually 270 degrees plus the size of angle Z must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. Okay, so again we will subtract from this equality 360 degrees and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that angle Z is a right angle, it equals to 90 degrees. So in quadrilateral DNSQ or DNSQ, we have four right angles, and any quadrilateral that has four right angles, it must be at least rectangle. Again, so quadrilateral DNSQ must be at least rectangle. Rectangle, if not square, it must be rectangle. At least rectangle. Okay, quadrilateral DNSQ must be at least rectangle. Quadrilateral DNSQ must be at least rectangle. And we have the rule that states that the opposite sides of any rectangle are equal to each other. The opposite sides of any rectangle are equal to each other. That is to say, SQ equals to DN. SQ equals to DN, that is the opposite side of SQ. SQ equals to DN. But we have already found out that SQ is the radius of this circle, of the big circle, that is to say it equals to 2R. So from this equality we will derive that dn also equals to 2R. dn also equals to 2R, and ds equals to the opposite sides of rectangle ds and q, that is to say it equals to nq. ds equals to nq according to the rule that the opposite sides of a rectangle are equal to each other. So dn equals to nq, but we know that nq equals to the radius of the big circle, that is to say it equals to 2r. So actually from this equality we will derive that ds equals to 2r, ds equals to 2r. So here ds equals to 2r. And we also know that DA or AD is one side of square ABCD, And we know that all the sides in any square are equal to each other. So here DA or AD equals to 8 units, because of the fact that all the sides of any square are equal to each other. So in square ABCD, side DA will be equal to 8 units. So what is the size of SA? Actually, SA equals to DA minus DS. Again, SA equals to DA minus DS. Okay, so I'll write it down. SA equals to DA minus DS. So SA equals to DA, that is 8 units, minus DS, that is 2R. So we found out that SA equals to 8 minus 2R. SA equals to 8 minus 2R. Okay. Again, we know that all 4 angles of a square are right angles, they are equal to 90 degrees. That is to say, angle BAD of square ABCD equals to 90 degrees. ABCD is a square, so all the angles of a square are equal to 90 degrees, are right angles. But what is the size of angle BAD? Angle BAD consists of 4 angles, so the sum of those 4 angles will be equal to the size of angle BAD. That is to say, alpha plus beta will be equal to angle BAD. Alpha plus beta is 2 alpha plus 2 beta equals to the size of angle BAD, that is actually 90 degrees. Okay? So according to equation number 1, 2 alpha plus 2 beta equals to 90 degrees. We will divide equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. We found out that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Okay? If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Okay, so tangent alpha plus beta equals to tangent 45 degrees. Tangent 45 degrees equals to 1. So we found out in equation number 1 that tangent alpha plus beta equals to 1. Okay? But we actually have trigonometric identity for the value of tangent alpha plus beta. So according to the following trigonometric identity, tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, so according to this trigonometric identity, we can substitute tangent alpha plus beta in equation number 1 by this expression that equals to tangent alpha plus beta. So we will do it now. So instead of tangent alpha plus beta, we will write down the value of tangent alpha plus beta according to the trigonometric identity. The value of tangent alpha plus beta is actually tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. And it is equals to 1. Okay, so this expression is actually tangent alpha plus beta equals to 1 because this specific expression equals to tangent alpha plus beta. So in the next step, we will calculate the values of tangent alpha and tangent beta from the drawing. Tangent alpha, if we focus on the right triangle, triangle APM, this right triangle, so triangle APM, tangent alpha is the relationship between the angle that it is in front of tangent alpha divided by the angle that is near the angle alpha. So it is actually PM over AM. I will repeat again. In the right triangle APM, tangent alpha equals to PM over AM. But what is the value of PM? The value of PM is R. What is the value of AM? AM equals to 8 minus R. So we found out that tangent alpha equals to R over 8 minus R. Okay, so what is the value of tangent beta? We will focus on the right triangle, triangle ASQ. So in the right triangle, triangle ASQ, tangent beta equals to SQ over AS. SQ over AS. Again, in the right triangle, triangle ASQ tangents beta equals to SQ over AS. Okay, tangents beta equals to, in the right angle ASQ, tangents beta equals to QS over AS, or SQ over AS. What is the value of SQ? The value of SQ is 2R, and the value of AS is 8 minus 2R. In total, we got that tangents beta equals to 2R over AS minus 2R. So we actually found out the values of tangents alpha and tangents beta. In the next step, we will substitute the values of tangents alpha and tangents beta in this equation number 1 by the values that we found for tangents alpha and tangents beta. Okay? So we will do it now. So in equation number 1 we have tangents alpha and we have already found out that tangents alpha equals to R over 8 minus R plus tangents beta. According to what we have already found, tangents beta equals to 2R over 8 minus 2R. And we will divide all by 1 minus tangents alpha times tangents beta. Tangents alpha is R over 8 minus R. And tangents beta is 2R over 8 minus R. All equals to 1. So we got this equation number 1 after we substituted tangents alpha and tangents beta by the values that we found for tangents alpha and tangents beta. We got this equality. We have one equation with one variable that is R. So it is very simple to solve this equation. Here we will make a common factor for these two expressions. The common factor will be 8 minus R times 8 minus 2R. And in order to get this expression, we will multiply R by 8 minus 2R. And in order to get this expression, we will multiply 2R by 8 minus R. Okay, so actually this expression equals exactly to this expression. Then we will take a common factor for these two, for 1 and this expression. In order to have a common factor for 1 and this expression, we will substitute 1 by 8 minus R over 8 minus R, that is actually 1, and 8 minus 2R over 8 minus 2R, that is also 1. So actually this expression equals to 1. Now we have a common factor. This is 1, we have a common factor with this expression. Okay, and what we have in the numerator, we have 2r squared. Okay, so here we have all equals to 1, of course. Here we will have to move this expression to the numerator, and after we will move this expression to the numerator, it will get cancelled with this expression, because it is actually 8 minus r times 8 minus 2r, and here we have also 8 minus r over 8 minus 2r. So actually this expression will get cancelled with this expression. So what is left after we cancel those two same expressions? For equation number 1, we have it left only with r times 8 minus 2r plus 2r times 8 minus r over 8 minus r times 8 minus 2r minus 2r squared, all equals to 1. Okay, so this is the expression that is left after we cancel those two expressions. So here we will open the brackets, or first of all we will cross multiply this expression. We will cross multiply this expression, so we will get that r 8 minus 2r plus 2r 8 minus r equals to 8 minus r times 8 minus 2r minus 2r squared. So we actually got this expression, equation number 1, after we cross multiplied this equation, and here we will open the brackets, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, and here 2r times 8 is 16r, 2r times minus r is minus 2r squared, all equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, and minus r times minus 2r is plus 2r squared, minus 2r squared. So here plus 2r squared minus 2r squared is 0. So those two expressions will get cancelled. So what is left after we cancel those two expressions is we have here 8r plus 16r is 24r minus 2r square is actually minus 4r square equals to 64 minus 16r square minus 8r is minus 40 minus 24r. That's all. So here we will subtract 24r from this equation number 1. And we will get that minus 4r squared equals to minus 48r plus 64. We will subtract 4r squared. We will add to this equation number 1 4r squared. We will get that 4r squared minus 48r plus 64 equals to 0. So here we have a quadratic equation. We will divide this quadratic equation by 4 and we will get that r squared minus 48 over 4 is minus 12r plus 64 over 4 is 16 equals to 0. So we have the quadratic equation that says that r squared minus 2r plus 16 equals to 0. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0 when a, b and c are the coefficients of this quadratic equation and x is the variable that we are looking for. And in order to find out the value of x, we have a special formula for x. X equals to minus b plus minus root of b squared minus 4 times a times c over 2a. Okay, so we will find out the value of x according to this special formula. Here a, b, c are the coefficients of the quadratic equation and x is the variable that we are looking for. Okay, so in our specific quadratic equation, I write it again, r squared minus 12r plus 16 equals to 0. First of all, the variable here that we are looking for is r, so x equals to r, a equals to 1, b equals to minus 12, and c equals to 16. So we will put the data inside this equation in order to find out the value of r. So x equals to r, so r equals to minus b, b equals to minus 12, so minus minus 12 is plus 12, plus minus root of b squared, b equals to minus 12, so minus 12 squared is 144, minus 4 times a is 1, so 4 times a, minus 4 times a is minus 4, minus 4 times minus 4 times 16 is minus 64, and all divided by 2a, that is 2. 2 times 1 is 2. So we actually have r equals to 12 plus minus root of 144 minus 64 is 80 over 2. Okay, so we actually got this expression r equals to 12 plus minus root 80 over 2 square root 80. 80 equals to 20 times 2, 20 times 4. 20 times 4 is 80, so I write it down. R equals to 12 plus minus root of 4 times 20 is 80 over 2. So the root of 4 is 2, square root of 4 is 2, so R equals to 12 plus minus 2 times root 20 over 2. So R equals to 12 over 2 is 6 and 2 over 2 is 1. So it's 6 plus root 20. 20 equals to 4 times 5. And the square root of 4 is 2, so we got actually that is plus minus R equals to 6 plus minus the root of 4 is 2 times root 5. So we found out that the radius of the small circle equals either to 6 plus 2 times root 5 or 6 minus 2 times root 5. R equals to 6 plus 2 times root 5, or R equals to 6 minus 2 times root 5. Okay, but we know that the size of one side of a square is square ABCD is 8 units, or AB that equals to all the other sides is equals to 8 units, and we also know that both the big circle and the small circle are inside the square. From the fact that they are inside the square, we will conclude that the radius, actually also the radius of the big circle, and let alone that the radius of also of the small circle must be smaller than the side of the square, because it is inside the square. So actually the radius must be less than 8 units. But here R that equals to 6 plus 2, R that equals to 6 plus 2 times root 5 is greater than 8 units. That is to say, this possibility is not correct because of the fact that the square is inside, the small circle is inside the square. So the radius of the small circle must be less than the length of one side of the square. Okay? So the only possibility that is left is that the radius of the small circle equals to 6 minus 2 times root 5. That is to say, it is about 1.53 units. Okay, so we found out that the radius of this small circle equals to either 6 minus 2 times root 5, or in terms of number, the radius of this small circle equals to 1.53 units. Okay? So now I'll summarize the lecture. Actually, we wanted to find out the radius of this small circle, and before we solved the question, I presented to you two rules. Okay? I presented to you two rules. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So the meaning of rule number one is that if the radius of this circle is drawn to the point of tangency, that is to say point O, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. Again, whenever the radius is drawn to the point of tangency, that is to say point O, then the tangent will be perpendicular to that radius, that is to say this angle is 90 degrees and this angle is 90 degrees. So that is rule number one. And I also presented to you rule number two. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. The meaning of rule number two is that if you have external points to this circle, point P is the external point to this circle, and if from this point, point P, you draw two tangents to this circle, then the length of those two tangents will be equal to each other. That is to say, AP will be equal to BP, or PA equals to PB. Okay? So if from external point of a circle you draw two tangents to this circle, to the circle, then the length of those two tangents will be equal to each other. That is to say AP equals to BP. That is rule number two. And then we actually proved that those two triangles can go into each other, because AM equals to AF. According to rule number two, from external point A, we have two tangents to the small circle, therefore they are equal to each other according to rule number two. AM equals to AF. And PM equals to PF equals to the radius of the circle, and AP is a common side, it belongs to both triangles. Therefore, triangle AMP is congruent to triangle APF according to side rule. And if this angle is alpha, this angle will be also equal to alpha, according to the rule that corresponding angles in congruent triangles are equal to each other. So both those two angles are equal to alpha. And we also proved that those two right triangles can go into each other. Again, AL equals to AS according to rule number 2. From external point A, we draw two tangents to the big circle. The length of those two tangents are equal to each other according to rule number 2. That is to say, AL equals to AS and QL equals to QS. They are both the radiuses of the big circle, and AQ is the common side. It belongs to both triangles, so AQ equals to AQ. From the fact that, so we proved that those two right triangles can go into each other according to side rule. And from the fact that they can go into each other, we will conclude that those two angles are equal to each other, and if this angle is beta, this angle will be also equal to beta. Okay, and we know that all the angles of a square are right angles, and especially this angle is a right angle. It equals to 90 degrees. That is to say, 2 alpha plus 2 beta equals to 90 degrees. And if 2 alpha plus 2 beta equals to 90 degrees, 2 alpha plus beta, 2 beta equals to 90 degrees, we will divide this equality by 2 and we will get that alpha plus beta equals to 45 degrees. If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Tangent 45 degrees is 1. So we got that tangent alpha plus beta equals to 1, and we have this trigonometric identity. So we will substitute tangent alpha plus beta by this expression, and we will get that this expression, and then we calculated the values of tangent alpha plus beta, the values of tangent alpha and tangent beta. Tangent alpha, according in this right triangle, equals to r over 8 minus r, and tangent beta in this right triangle equals to 2r over 8 minus 2r. And we substituted, so tangent alpha equals to r over 8 minus r, and tangent beta equals to 2r over 8 minus 2r. Okay? So we substituted tangent alpha by r over 8 minus r, and we substituted tangent beta in this equation number 1 by 2r over 8 minus r, and we got this equation, and we solve this equation, and we add two solutions to the quadratic equation. The first solution was that r equals to 6 plus 2 times root 5, but because of the fact that the size of one side of square ABCD is 8 units, and both two circles are inside the square, the radius of the small circle must be less than the size of one side of the square. That is to say, the radius of the small circle must be less than 8 units. And this answer that the radius of the small circle is greater than 8 units is incorrect answer, because the radius must be less than 8 units. So the only answer that is left, that the radius of the small circle equals to 6 minus 2 times root 5 units, or the radius of the small circle equals to 1.53 units. Again, the radius of this small circle is either equal to 6 minus 2 times root 5 units, or in terms of number, the radius, in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so that is actually the answer to the question. Okay, the radius of the small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, it equals to 1.53 units. Okay, thank you very much.